Welcome back. Let's talk about graph theory. Okay, first let's start off with some nomenclature. So nomenclature is just a fancy word for names of things. By the way, I'm sort of using these pages of the notes to kind of guide what I'm talking about here. So you might want to pull these up, the graph section in the class notes that's already posted. So let's see, we have nodes. Here's two nodes. And then we have edges that connect those nodes. There's an edge. Okay, you could have even more. So here's another node and another edge. So this is called an unweighted, undirected graph because the edges have no values on them and they have no direction. That is, they have no arrowhead on them. So it's unweighted and undirected. We could add weights. So you could put, say, a 5 on here, and you could even put a direction. And maybe put a 10 on here going that way and a 2 going that way. So this is a weighted and directed graph. Okay, so we have nodes and edges, and graphs are kind of a special case of a tree, if you see. I mean, a tree has nodes and edges. They're typically unweighted, but there's other restrictions on a tree, like each parent has so many children and, other restrictions like that. Anyway, but before we go on, I think it's good to sort of back way up, kind of a high level concept here. There's this idea of data organization and task. So you could think of this as maybe nouns and verbs. Okay, so for example, we've been looking at different data structures and then looking at algorithms that operate on those data structures. So what have we done so far? We have an array, right? That's what we started with, like first week of the class, right? And what did we do to that? Well, we did a bubble sort. Okay, so if you organize your data into an array, then there's certain things that you can do to it. Like you could sort it, maybe you could search it with a linear search, or if it was already sorted, you could do a binary search. There's other things that you could do, but it's just an idea of a certain data organization yields lends itself towards certain kinds of tasks that you might want to do. All right, then what did we look at? We looked at some other things, but we looked at a stack, right? That has certain operations, push and pop, right? And queues and other things. And then we looked at a tree. So trees are very good for searching and some other things. So what about graphs? Well, graphs, mostly we're interested in various kinds of pathfinding tasks, more or less. Okay? So I just thought it'd be good to just re-emphasize this idea of data organization, or nouns, if you like, and the tasks that you perform on those things. So what about graphs? Well, what can we use graphs for? Here's some applications just out of the notes. There's you can represent the state of a process, like let's say you could have ice, and then maybe you move to water, and then you move to steam. So this is like the 3 states of matter. But you could also, when establishing an IP, Internet Protocol connection, there's a init, and there's real simplified, there's like wait, there's some other states in there, and then you're at a, like, there might be an acknowledge, and then you're in a connect state. It's a little more complicated than this, but there's these different states that you go through before you have a connection. Okay, so graphs are and it does go off into some other, just to show you that it is a more complicated graph. It goes off in kind of weird directions, and you could look that up if you're interested. But it is a graph. There's something called the map coloring problem. So you got the USA, and then you got Canada up here, and then you got Mexico, and then Mexico's got a bunch of countries that it's connected to. I don't even know how many, and then they end up coming back down to Panama, right? So if you were going to color this, you might want to make this red, and then blue, and then so now you can't use you can't use blue here. You could use green, right? And maybe you could use yellow, but you can't use blue. You could use red again, like that. And then down for Panama, well, you can't use red, yellow, or green, but you could use blue, like that. So there's the map coloring problem. Okay. Okay. Then there's something called the traveling salesman problem. So we've got state. IP connection is a kind of is a state diagram. You could have a state of matter, and you could have state of IP connections. You could have the map coloring problem, and then there's something called the traveling salesman problem. So there's variations on this, and let's see. Let's set up a little. So let's say we've got LA, and then we've got San Francisco, and then we've got Seattle, and maybe we've got Denver. Okay, maybe we've got Houston and Dallas. Okay, so there could be weights on here. Like I say, it costs $100 to go that way on an airline flight, and it costs $200 to go that way. So the traveling salesman problem has many variations. You could be interested in the fewest hops. Like maybe there's a direct flight from LA to Seattle that costs $500, right? So you might be interested in the fewest hops. So LA to Seattle, you do the direct flight because it's one hop. But you might be, instead of fewest hops, you might be interested in cheapest cost. So if you go through San Francisco, from LA to San Francisco, then to Seattle, then that's only $300, right? It's $200 for this leg. Well, let's say this leg goes both ways here with the arrow, and then $100 for that leg. So maybe it's cheaper, but you have a layover, right? So these are different versions of the traveling salesman problem. Another one is maybe you want to visit all nodes. That could be another problem that you want to solve. You want to visit all nodes, maybe the least cost, or maybe you want to do it in the least total distance or something. Who knows? Because maybe you don't want to fly back and forth. You want to kind of fly short. So there's variations on the traveling salesman problem depending on what you're most interested in. A good example of that is in actual networks. They're like, let's say this was an Ethernet, or not an Ethernet, but a fiber optic network or something cross country. There might be a latency period, a latency time. Like maybe this has a 500 millisecond latency, but this one over here has, say, a 20 millisecond latency, and this one here has a 20 millisecond latency. Maybe, but it could be more expensive. This could be $50, and this could be $50, but maybe this is only $40. It'd have to be more than 100, right? maybe $120 or something. So this would be, well, this is better. Well, I make it less. So this 50/50 is 100. Let's make this $75. Okay. So if you go, let's say you're trying to go San Francisco to Dallas, and you're interested in the least dollar cost. Well, that would be this link here because it's 75. Wait, so I mixed that up again, didn't I? This should be, let's make it $150. Yeah. So the cheapest, what am I doing here? I'm getting confused here. $75. So if you go, this is $75, this is $100, but this is $40. Yeah, okay. So this one here, if you go up San Francisco to Denver to Dallas, it's going to be $100 total, but it'll be 40 milliseconds total. So it has a higher dollar cost, but a cheaper latency. It's faster. And this link here is 75, so it's cheaper in dollars, but it has a higher latency, so it's slower. So anyway, there's variations on the overall problem that you're trying to solve, and then there's different definitions of best. It could be latency, could be dollar cost, could be number of hops. All right. So we'll look at a couple algorithms in particular for graphs, but the first thing to talk about, or the next thing to talk about rather, is some implementation basics. So first, memory. Like, how are you going to store this thing? There's basically two ways. There's an adjacency matrix or a table. This would just be a two-dimensional array. That's the simplest way to do it, right? A two-dimensional array. Matrix, 2D array. Okay, you could do that, or you could do an adjacency list, and these could be links. So this first row here could be an array of nodes. And then each one of those nodes has a link coming off of it. In other words, something like, let's see, what do I got here? I got, like what is this thing right here? Let's see. It could be struct node. You could have integer key. And then you could have node pointer next. And then you'd make an array of nodes. Guess you could call it root, and make it, let's see, 1, 2, 3, 4, 5. Make it 5 elements long. So something like this. So you'd have an array of these nodes, and each one of these nodes would have a list built off of it, something like that. Whereas this over here is just it's just a two-dimensional array. 1, 2, 3, 4, 5 by 5 array. All right. So what are these have pros and cons. So first of all, just look at what's in here. So here's a graph I got. This is just sort of a random graph I made up, A, B, C, D, E, and are the nodes, and then they have these edges on there. So what we're storing in the table is each node's neighbor. So we have A, B, C, D, E. That's each node, A, B, C, D, E, and then for each row we have that node's neighbor. So for row A, A has neighbor B and a neighbor D. So we put a mark on column B and column D. Okay, so A has neighbors B and D, and like that for all of them. So B has neighbors A and C, or you could say that B is adjacent to A and C. right? B's neighbors are A and C. So B is, you put a mark by A and a mark by C. Okay, and D has neighbors, oh, I skipped C. C has neighbors B, D, and E. So you put a mark B, D, and E, and D has neighbors A, C, and E. So we mark A, C, and E, and E has neighbors C and D. Okay, so this is good if you have lots of edges, right? Because imagine if you didn't have a lot of edges, you'd have a lot of blank spots, right? And you'd be wasting space. Okay, so a matrix is basically good for a dense graph. Dense. And by dense, I mean lots of edges. It's a good, efficient use of memory, that is, if you have lots of edges. Okay, then another way to do it is this array of nodes, and then build a list for your neighbors. So A's neighbors are D and B, right? A's neighbors are D and B right here. And B's neighbors are A, C. B's neighbors are A and C. Up here, backing up for a minute, A's neighbors are D and B. It would probably be better to put them in alphabetical order. The D and B. It really it should be B and D, but it doesn't really matter. It just bothers me a little looking at it now because the nerd in me, and I want to make these alphabetical, but it doesn't really matter. Okay, it's just a list of neighbors in any particular order, really. So C has neighbors B, D, and E, right? So I've got B, D, and E. C has a list hanging off of him of all his neighbors. Okay, which is better? Well, it just depends on how dense the graph is. If it's very dense, then a matrix is a efficient way to store them. And if it's if the edges are if there's not very many edges, that is to say, if the graph is sparse, then an adjacency list will be more efficient, right? But look at this list here. You've got all these. You've got the keys. And then you've got a node. So you're wasting space on these nodes, which is fine if there's not very many neighbors. But if there's a lot of neighbors, then you're going to basically double the data, right? If every node was connected to every other node, you'd have twice as much data in the adjacency list as you would in the matrix. Okay, so there's efficiency of space is the issue. So a list is good for sparse arrays. But there's one other thing. A matrix is just easier to code. So in the homework implementation I'm using a matrix. And it's not really a space efficiency thing. It's just that it's easy to get in here. And like if it was a list, you'd have to use the new operator and the delete operator. You have to deal with dynamic memory and clean pointers and all this stuff. If you built a library, to do those operations for you, it wouldn't be so bad. But just to make it simpler so that we can concentrate on the traveling salesman problems, variations, we're going to use a matrix. Okay.